Hello and welcome to the Core Pure 1 video on volumes of revolution. So we're given a formula here for the volume of revolution, and it's in your booklet. The volume of revolution of a curve is equal to pi times the integral of y squared dx if we rotate about the x-axis, and pi multiplied by the integral of x squared dy if we rotate about the y-axis. Let's just check what we mean by volume of revolution. So I'll come on to these two examples in a minute. If you have a curve, say a curve like that, and you spin that curve around the x-axis, so we rotate that curve round, so it's not a brilliant diagram, but it gives you the idea. We get this sort of trumpet shape here, and we could want to find the volume of this shape when it's a solid shape. If we know the equation of the curve, we can use these formulae to work it out. So let's do these two examples and see how that works out. So we've got here a curve. In fact, it's a straight line. The line y equals a half of x. We're considering it from x equals 0 up to x equals 4, and we're rotating it about the x-axis. So that's actually going to produce a cone. So this is drawn in 2 dimensions, but it's actually a cone like this. So applying this formula, we've rotated about the x-axis, so the volume is going to be given by pi times the integral of y squared dx. So we can start by writing the formula just to help us learn it, and then substitute in the actual function we're using. So we've got y is a half x, so when we square that, we're going to get a quarter x squared dx. The two limits we're going to use are 4 and 0, so we're going to integrate between 4 and 0 here. So looking at that, that's going to be equal to pi. So that's going to be x cubed over 12 between 4 and 0. I'm going to evaluate that. Have pi on 64 over 12 minus, let's use my round brackets here, 0. I muddle with my brackets, and that's equal to, this is going to cancel, 32 pi over 6, and then that cancels again to 16 pi over 3. And that's the volume of the sphere, the cone that we produced here. Moving on to the next example. This time we've got a curve. So this time we've got y equals x squared, and we're rotating it about the x-axis. Always check which axis you're rotating about. And we are interested between 0 and 2, so this section here. So again, the volume of revolution is given by pi times the integral of y squared dx. And in this example, that is pi multiplied by the integral of, now y squared. So we want to square the function we've been given, so that's going to be x to the 4 dx between 2 and 0. And notice how important it is that we've got the dx here, because when we do examples rotating about the y-axis, we're going to be using dy. So it's very important that you're clear and use correct notation throughout these questions. So integrating x to the 4, we're going to get x to the power of 5 over 5. And we're going to evaluate that between 2 and 0. So that's going to be pi multiplied by 2 to the 5 over 5 minus 0 over 5. And when you evaluate that, you get 32 pi over 5. In both these examples, the lower limit was 0, but it doesn't have to be 0. We'll see that in the next example. We could have, in this example here, rotated the curve, just the section from x equals 1 up to x equals 5. And then we would have had this sort of shape here, a sort of section. It's not very well drawn, but a section of it. And then it would matter very much that you were putting in the correct limits and doing the subtraction here. So just bear that in mind as you work this out. So the final example we're going to do is when we actually rotate about the y-axis. So you're always, in these questions, I would advise doing a diagram just to help you see what's going on. So we're looking at y equals 2x squared plus 1. So just a quick sketch of that. So y equals x squared is going to look like that. So 2x squared plus 1 looks something like that, just to get the shape of it. So we've got x this way, obviously, and y this way. We want to rotate this about the y-axis, so it's going to go this way round. So we're going to get a disc with sloping sides at the edges here. And we're going to look at the section from y equals 2 up to y equals 5. So this, just this portion here, is going to be rotated around the y-axis. So start off writing out the formula. So it's going to be pi x squared dy, because we're rotating about the y-axis. So let's see how we're going to get that. We need x squared. Well, look at the equation here. We know that y is equal to 2x squared plus 1. We need to have this in terms of y because we're integrating with respect to y. So if we rearrange this, we get y minus 1. Half of that is equal to x squared. So I've rearranged the equation of the curve to get what x squared is equal to. So then substitute that in. The volume of this is going to be pi multiplied by a half y minus 1 in a bracket dy. And we're going to be doing that integration between 5 and 2, the two y values. So let's see what we get when we do this. This is equal to pi over 2. Now I can take that half. Remember, you can take any constant out of an integral sign. So I'm taking that half out to go with the pi. This is going to be y squared over 2 minus y. And I want to evaluate that between 5 and 2. So this is going to be equal to pi over 2. Then show carefully that you've substituted in 5 squared over 2 minus 5. Take away 2 squared over 2 minus 2. And when you work that out, you end up with 15 pi over 4. So that's the volume of this disc when it's rotated around the y-axis.